Hello YouTube! So today we're going to be talking about how to do equations when the calculus is a little more tricky and I guess a little less sort of just cut and dry on what you're supposed to do. I will try to break down the stuff that you're doing into something somewhat procedural, but still at the end of the day, a decent chunk of it's just going to be like, this is what you're going for. It kind of has to be somewhat instinctive, which is something you'll gradually build over time as you do more problems. So let's dive in. In particular, we're still working on using equations to model motion. And specifically for this one, if you can find local extrema, meaning places where it's locally big or locally small, or if you can figure out total distance traveled for an object using equations instead of a graph, because that can be a lot harder because it's a lot more involved to tell when it'll be going forward or backwards, when it turns around, all that jazz. So that's our goal. So in particular, zeros in most forms of math tend to be really, really important, and my face is in the way. My face is slightly less in the way. And in particular, if a function is equal to 0, that means that sort of definitionally, that function is either going to be crossing an axis or touching an axis for some reason, right? Because if our graph looks like this, and our function looks like this, we've crossed the 0 when we hit here. So we've either gone from positive to negative, or we've gone from negative to positive, or in a couple of rare cases, we'll just barely dip down and clip it, as it just barely touches 0. That last one is going to be kind of weird, and we're not going to deal with that a whole lot, but the first one, and the second one, where we're crossing the axis because we're going from positive to negative or negative to positive, winds up having a lot of implications. So the first derivative test is where you're taking the derivative of a function and you're figuring out where it's equal to 0. So basically you set the left side of the equation equal to 0, take the derivative of the right side, although normally you flip the order on that, and then solve for that. And what that'll tell you is all of the places where your function has a slope of 0. Now this is super relevant because if we look back at this graph over here, and this is something that I think I mentioned last time, the places where this function has a slope of 0 are the places where this function looks flat. So that would in particular be like here. It would be like here. And if you'll notice, because 0 means we're either crossing from positive to negative or negative to positive, in most cases, not all, what that'll mean, again, in most cases, not all, is that we're at a point where our slope has gone from being negative, meaning we're decreasing, to being positive, meaning we're increasing. Or our slope has gone from being positive, meaning we're increasing, to being negative, meaning we're decreasing, and we're just barely crossing between those two things. And that matters particularly because those will be the places where you turn around, which means it's either the highest up you are on the graph or the furthest down you are on the graph, meaning it's these extreme places. Hence, they're called extrema. The other option for that would be some weird form of inflection point where you have an inflection point that doesn't look like this. You have an inflection point that looks like this one does. And this would be caused by something like that weird, like it's just barely dipping and touching the 0, where we have a slope where our function of our derivative is positive the whole time. So it's still going up, but it's getting smaller. And then it's still positive, but it's getting bigger, so we get steeper as time goes on. So that would be the first derivative test. What you can then do for a second derivative test is once you've found all the places where the first derivative equals 0. So if you're like, okay, x prime equals 0 at 3 seconds and 5 seconds. What you can then do from there is take the second derivative. Why this is so useful is because if, this should be negative. I accidentally put the same sign twice. The reason why that second derivative test is so useful is because if you're thinking about what's happening to the function that is x prime, if we're looking at x prime and it's 0, and we're crossing from positive to negative, versus if we're crossing from negative to positive. In this first case, our slope is negative. meaning our derivative is negative. So if our second derivative is negative, then what all that will mean is that our function used to be positive and then becomes negative. Again, we're talking about the value of the function here, not the derivative. The derivative is negative the whole time. Our function used to be negative, then it's positive. Or sorry, positive, then it's negative. That means we used to be going up, and now we're going down. So if your second derivative is negative at a point where your first derivative is 0, that point is a local maximum because, again, you've gone from having a positive slope to having a negative slope on your original function. If it's the opposite, if you've got a positive slope on your first derivative, it means that your second derivative is positive because the slope of your first derivative will be the value of your second derivative. And because the value, you're crossing through 0 with a positive slope, it means you've gone from having a negative value to having a positive value, which means you've gone from a function where your slope is negative going down to a slope where function where your slope is positive for the original x function going up, which means you get this sort of dip giving you a local minimum. Last thing, if you want to find the time range where something is positive or negative, so a lot of times questions will be like, when is the object moving forward? When is it moving backwards? And so in order to do that, you would need to know when the velocity is positive or when the velocity is negative. All you have to do is find the time range where it's positive, is set it equal to 0. Once you've got it equal to 0, between all of those 0 points, plug in a random number into the original function. If the number is 0, is positive between those 0 points, that's only possible if you are positive the entire time throughout. Because if you're thinking about how the function is set up, let's say your function looks like this. I can't go from being positive to being negative unless I cross through 0. Now, this is only for continuous functions, which are the only functions that we should be working with. Just as a little caveat to that. But what that then means is that if I plug in a point here and literally anywhere in this time range, hello cat, goodbye cat, and that point is positive, between these 2 points, it would have had to be positive the entire time. Whereas between these 2 points, it's negative the entire time. Anywhere to the left of this, it's positive. Anywhere to the right of this, it's negative. And so again, if we've solved for all the places where it crosses the axis, as long as we know if it's positive or negative to the right or left of those places, we're good to go. So taking that and actually putting it into practice at least a little. Let's say we've got a function where the motion of our object is described by x equals 1/2 t to the third minus 3t plus 2. Great. What's the furthest the object travels from the origin? So this will be looking for a local minimum or maximum. In this case, a local maximum. When is the object traveling forward? When is the object traveling backwards is implicit within that, but it's just asking when it's traveling forward. So that would be when the velocity is positive. And what is the average speed of the object over the first 10 seconds of travel? That last one, we need to know how to find the total distance traveled, which we'll hold off on for a bit. So taking a sec to copy that down. This screen. We've got, this is 1 point something, nuanced calculus, physics C. Problem 1. Our equation is x is equal to 1/2 t to the third minus 3t plus 2. And for A, we're looking for max. For B, it just occurred to me, this is probably going to be one that, yeah, I messed up. I'm actually going to change this one to minimum. That wouldn't do it either. So the problem that I'm going to run into is that this function is going to be a t to the third function, so it'll look something vaguely like this. There will be no upper limit and there'll be no lower limit to the function. We should be able to find a local maximum though. So let's just find a local maximum instead. And then for B, when is the object traveling forward? And then for C, which we'll get to eventually, but not yet, average velocity. And that's from 0 to 10 seconds. Whoops. Sorry about smacking the mic there. All right. So let's do it. If we want to find local maxima or minima, we need to find the places where our derivative is equal to 0, because those will be the places where in the equation it looks something like this. So taking our derivative of our function for a, we've got x equals 1/2 t to the third minus 3t plus 2. We're looking for the derivative with respect to time, which I really should grab another colored pen for. And we've got dx dt over here as well. dx dt is equal to velocity. On the right half, we've got 1/2 t to the third, so we drop the power by 1, drop that original power of 3 over here, so we'll get 3/2, minus 3, drop the power by 1, t to the 0 is the 0, 3 times 1 is still 3. T to the 0, drop the power, t to the -1, we've got the 0 still hanging around from t to the 0, so nothing here. And that'll get us this friendo. So this is our velocity function. The maxima slash minima will be at velocity equals 0. So I'm going to go ahead and plug in 0 for my velocity and then solve. I'm also going to apparently drop my pen. Great. So we've got 0 equals 3/2 t squared minus 3. So now we just need to solve. In particular, something you want to be careful of for these, plus 3 to both sides, is that there's going to wind up being 2 solutions if you have a squared. Sometimes one of those solutions will just be 0. Occasionally you'll get only one solution for something like that, but it shouldn't happen often. So just as you're doing this, be aware that your final answer should probably have 2 solutions. We've got a 3/2 that's being multiplied. The opposite of that would be division. So we multiply it by the reciprocal. And that will give us 2 is equal to t squared. Square root both sides, and when you square root the side without a square, just remember that it'll give you back a plus or minus. And so what we're left with here is plus or minus root 2 are the times at which we'll have local maxima or minima. So now what we need to do, in order to figure out whether or not they're maxima or minima, is a second derivative test. So this is our first derivative test. Hello. And then for our second derivative test, we need to take our velocity function, which was 3/2 t squared minus 3, and take the derivative of that with respect to time. The derivative of velocity with respect to time is acceleration. If you want to write x double prime instead, that works too. Derivative of t squared is t times 2, so 3 times 2 over 2 is just 3, t minus nothing. Gets rid of our constant when we take the derivative. And for our second derivative test, we just have to plug in these 2 times, plus or minus root 2. When we do that, we'll get that at our extrema, so at plus root 2, we'll get positive 3 root 2. At minus root 2, we'll get that our acceleration is equal to negative 3 root 2. Because our acceleration here is positive, it means that we're going to be moving forward after this. We're at rest right now, and we have a forward acceleration, so we'll be moving forward afterwards. If we're at the bottom and about to start moving, if we're about to start moving positively, that means that we're currently at a 0 line at the bottom. So this is a minimum. The flip will be true for this next one that's negative. So our local maximum will be at t equals negative root 2. We're not asked for when the object is the furthest it travels from the origin locally. What we're asked for is the value of that. So what we need to do is take this and, final step, plug it back into the original equation, because we're asked for a position. So we'll have 1/2 times root 2 to the third minus 3 root 2 plus 2, which 1/2 over root 2 to the third is going to be 2 times root 2 divided by 1/2, because 2 squared, root 2 squared is 2. So that gives us just root 2 minus 3 times root 2 is negative 2 root 2 plus 2 meters, and there's our answer. Actually, we should be careful here. So thinking about this, especially because this winds up being a negative number and it's about to start getting further negative, this isn't the furthest it is from the origin. This is the furthest it locally is, the most positive it is locally. If we're asked from the furthest from the origin, we actually should probably check the other point, which my guess is, because this is about to start going down, with the negative acceleration and it being at rest, this is actually going to get lower, because this is a negative number. 2 times root 2 is bigger than 1, so 2 times root 2 is bigger than just 2 times 1. I actually do need to check the local minimum. The local minimum will probably wind up being a greater negative number. So just checking what our function looks like, it probably looks something like this, where it's under the axis the whole time. So this would actually be locally where it is furthest from the origin. We're going to need these points for point C anyway, so there's no real worry or extra effort in double checking by calculating it now. Anyway, so if I go ahead and take that second time and plug it in, we'll get x equals positive root 2 to the third minus 3 times root 2 plus 2. And at that point, what we'll wind up with is I just realized I did this wrong. I should have plugged in negative root 2 here. So this should be positive. This should be negative. This should be positive. And we're good. So this is above the axis. But again, because it was asking about from the origin, that will probably wind up being the answer, but we should double check with the second point anyway, which again will wind up being useful eventually. So plugging in the positive, we'll actually get the thing that we got last time, which is that we'll have root 2 to the third. So again, that's 2 root 2 minus, but being divided by 2 is just root 2 minus 3 times root 2 plus 2. And so that'll give us negative 2 root 2 plus 2. And that's our sort of second location. These two are adding together, so they will make a number with a greater absolute value, whereas these two are subtracting, so you can think of that as fighting against each other. This one will wind up being closer to the origin than the other, so we were right with our answer the first time. Again, this is useful for part C. For B, they're asking us when the object is traveling forward. To figure that out, all we need to do is take our information we already have. Velocity equals 0 at the 2 times of plus or minus root 2. So what I can do are take the 3 time zones that exist around these points. If I think about my velocity function, it should look something like this. Here it's a 0. Here it's a 0. What I need to do is find out whether or not it's positive or negative between those 2 points and on either end of those 2 points. So I can just take some numbers and plug them into the velocity equation. The velocity equation was right here, 3/2 t squared minus 3. And I can plug in 3 values. I'm going to pick 3 that seem pretty easy to me to plug in. I'm going to pick -2, 0, and +2. As long as it's between to definitely lower than negative root 2, definitely higher than positive root 2, and between negative root 2 and positive root 2, you're good. Plugging in -2, we've got velocity equals 3/2 times -2, remembering the negative this time, to the squared. Of course, it won't matter. Which gives us 4 times 3 over 2, which is 6, minus 3, which is +3. So this is at -2. That tells us that over here, our graph is positive. For 0, which is the between point, we've got v equals 0, because we've plugged in 0 for t squared, minus 3, so -3. So for t equals 0, it's negative. So between these 2 points, our velocity is negative. Plugging in +2, -2 and +2 squared are the same thing. So we'll still get 4 times 3/2, which is still 6, so +3. So in this section, our graph is positive. So we've got positive, negative, positive. So our object is moving forward before negative root 2 seconds and after positive root 2 seconds. And those are our times our object is moving forward, because those are our times where we have a positive velocity. If we want to do part C, where we're being asked about whether what the average speed is, we're going to have to actually use our average speed equation. Now, previously, we've basically used that our average speed equation is our total distance traveled between any 2 points, and then divide that by the time. So our goal for this one is going to be find our extrema. We've already done that, great. And we can basically say, okay, well, wherever it starts to the first extrema, find the distance traveled between those two, because it can't turn around without having an extrema. So if it can't turn around, even if it's doing something wonky with the curves, it's still either always going to be moving forward or always going to be moving backwards. So the total distance traveled and the displacement between those 2 points will have the same magnitude. If you do that for each extrema, and you also do that including the start time of the range and the end time of the range as 2 extrema, that will give you the displacements from each section. The displacements from each section, their magnitude will give you the distance from each section, which you can then add to get your total distance traveled, which you can divide by the time and be all set. So doing that for this one, which I've already done a decent chunk of the workout for, I'm still going to need, so my extrema were at positive root 2 seconds, which is the only one between our time range of 0 and 10 seconds. And the value for that one was -2 root 2 plus 2. At 0, our equation is nice and easy. -3 times 0 plus 2, which is just 2. So we're starting from +2 and we're going down to this. At 10, we've got x equals 1/2 times 10 to the third minus 3 times 10 plus 2, which is going to be 500 minus 30 plus 2, which is 472, I believe. What I can do is then combine these 3. We go down from here to here. So my displacement for this first section is the time at the later section minus the time at the first section. So this is our final position minus our initial position, which will give me negative root 2 negative 2 root 2. So for our first section, this is our distance traveled. For our second section, we do the same thing. Our final velocity minus our initial velocity. Our final position for the second section is 472. From there, we can subtract our negative 2 root 2 plus 2, which will give us 470 plus 2 root 2. For our total distance traveled, we have to add these two magnitudes. So very, very careful to keep it as a magnitude. So we'll have 470 plus 2 root 2 plus our 2 root 2 from our first section. I'm making it positive because I only want the magnitude. This will give us 470 plus 4 root 2, combining like terms, and that's our distance. To get our speed, all we need to do is take our distance and divide it by our time. So it'll be this number of 470 plus 4 root 2 over 10. If you want to leave it like that, that is fine by me. Meters per second. A calculator will also tell you what it is, but I am lazy. This video is getting long, so I'm going to call it. Goodbye, YouTube. Throw any questions in the comments, as always. Hope you have a great day.